Hi everyone, hope you enjoyed your lunch. We are still here. Today the very first guest will be Silvia Caligari from the joint PhD program between University of Pavia and UC. And she will talk about the FSI problem with active force for cardiac models. Okay.
Thank you for your presentation. Welcome everyone. Okay, today I would like to talk with you about FSI problem with active force for cardiac models. This is a joint work with Maria Nestola, Marco Favino and Professor Ralph Krause of the Italian SUS University of Lugano. Okay, we talk about cardiac models on Tuesday morning thanks to the brilliant course of Mai and Nicholas. So, okay. Okay, thank you. So, take a deep breath and let me briefly recap. We have three different physics: the electrophysiology, the active and passive mechanics, and the fluid dynamics. Why? Okay, we have an electrical signal which starts in the sinoatrial node and go through all the cardiac tissue. So we talk about the electrophysiology. Then we have muscle contraction. So we talk about active and passive mechanics of the heart. And the heart is full of blood and is covered of blood vessels. So we have fluid dynamics. All these three physics have to communicate each other. And so the idea is to have a fully coupled model which represents all these physics and their communication. We will start from electrophysiology. So we want to create an app which describes a model of the electrophysiology. Then we will talk about the fluid and structure interaction thanks to a novel framework published by the University of Lugano. So we have the communication of mechanics and the fluid. And lastly, we want to insert in the FSI interaction the electromechanics through an active force. Okay, in a cardiac cell, we have a different concentration of ions. So ions represent a charge. Where there's a charge, there's an electric potential. So we have an electric potential intra the cells and outside the cells. So we will have an intracellular potential and an extracellular potential. The most complete model that describes this electrical signal is the B-domain model, which describes the intra and the extracellular potential through two degenerate parabolic reaction diffusion equation. And this system is coupled with a system of ordinary differential equation describing the ionic currents, and the opening and the closing of the ionic channel that are responsible of the inflow and the outflows of the ion inside and outside the cells. For our simulation, we introduced the Monodomain system, which is a simplified model and is less expensive in terms of computational cost. Our Monodomain system is coupled with the Luo-Rudy ionic model, which consists of 6 different ionic currents. One represented the sodium, the potassium, and also includes the dynamic of calcium, which is strictly connected to the muscle contraction. For this, the space discretization, we use a finite element method, in particular a first-order elements. And for time discretization, we use the Rush-Larsen method for the implementation of the ordinary differential equation. Then we have the solution of the ordinary differential equation, and we use it for the solving of the monodomain system. Okay, so we build our app describing the electrophysiology using an open source framework called MOOS. In the first frame, you can see in a two-dimensional domain, we consider at the resting value of the potential, which is about minus 84 millivolt. In the second frame, you can see the wavefront of the electric signal, and in the last frame, there's the repolarization phase, so the phase when the electric potential returns to its resting values. Okay, so we have the app for the electrophysiology. Now we want to introduce the second tools of our work, which is the framework that describes the fluid structure interaction which is published by the Rolf-Krause group at the University of Lugano, and consists of a framework that has three different characteristics: the solution of the elastodynamic equation, a nite solver for the fluid equation, and a two-projection transfer, which is able to communicate from the solid to the fluid and to the fluid to the solid. Okay, so we have two different domains, the domain regarding the solid and the domain regarding the fluid, with different configuration and different mesh. Then we have a boundary, two different boundaries disjoint, one regarding the solid or the fluid, and one regarding the interfaction. So, let's start from the solid subproblem. We have the elastodynamic equation. For the fluid subproblem, we have the Navier-Stokes equation. And for the interface, we want to impose a continuity of two variables, the velocity and the force. So we want that the velocity of the fluid on the interface must be equal to the velocity of the solid, and the tension of that is applied from the solid to the fluid must be equal. Okay, for the discretization of our model, we use a finite element method for the space discretization, and the residual of the weak form can represent the force applied from the solid to the fluid, and we will use it to solve the Navier-Stokes equation. Then, for the fluid, we consider two different grids, so they are staggered grid, one for the pressure and one for the velocity. And the discrete operator of Laplacian, the gradient, and the divergent operate on this grid. In particular, the divergence and the gradient operate on a grid, taking values from the others, and only the Laplace operator is applied on only a grid. Okay, for time discretization, we use a fully implicit method for the solve of the solid problem. Then a third-order Runge-Kutta scheme for the solves of the fluid problem. And then we use an iterative method for the solving of the coupling between the solid and the fluid. And this solver ends when one of the two convergent criteria is satisfied. We have an absolute convergent criteria and a relative convergent criteria. How does it work with this algorithm? We start from the initialization of our variables, in particular the initialization of the velocity of the fluid. Then we transfer the velocity of the fluid to the solid, thanks to the operator published by the University of Lugano, which is based on L2 projection and immersed boundary. Then we evaluate the displacement of the solid, thanks to the velocity. Then we solve the elastodynamic equation, and we evaluate the forces exerted from the solid to the fluid, and we use it for we transfer it into the fluid, and we solve the Navier-Stokes equation. And if one of the two criteria is satisfied, we update the solution. Okay, how can we use this framework? With a simple, for example, benchmark, which is the Frankfurt benchmark. So we have a beam into a fluid, and we can see the movement of the oscillation of that beam, and it represents the velocity along the x direction of the fluid. But this framework is also used from the University of Lugano in collaboration of the University of Berna and the Cardio Center of Ticino for simulation about heart valves, and in particular for simulation for some particular disease of valves. Okay, so I repeat, we have an app for the electrophysiology, we have a framework for the fluid-structure interaction. Now we want that there is a connection between the electrophysiology and the fluid-structure interaction. How can we build this connection? Using an active stress, which represents the muscle contraction. Because we have the dynamical calcium, which is strictly connected to the muscle contraction, and so we have the connection between the mechanic and the fluid. So let's consider for a moment only the structure and introduce an active stress. This active stress is modeled by a function which is periodic, like an heartbeat. So there's a contraction and there's a stretch of the structure. Okay, insert this active stress into the FSI framework, so into the fluid. Okay, so we have the mesh of the structure for the FSI problem, only the FSI problem, which is blue, and the red mesh represents the mesh of the structure where we add the active stress. And in this framework, in this zoom of the framework, we can see a stretch of the structure. Okay, if we proceed the simulation, there's a contraction of the structure, and then in the last frame is more evident the presence of the oscillation, so the presence of the fluid. So we combine two movements, the oscillation due to the fluid and the contraction due to the active stress. Okay, now I can show you the structure into the fluid. Also in this case it represents the velocity of the fluid along the x direction, and the structure which contraction and stretch and the oscillation. Okay, thank you. I hope you enjoy my presentation, and thank you for your patience and your attention.
Thank you very much. Anybody of you has questions?
If not, I will ask a question.
Let us start from me. No, I was.
Thank you, Silvia, for the nice presentation. Can you go back to this FSI space discretization? Because if I understood well, but you can correct me if I suppose you can correct me. So you have two kind of different configurations, right? One for the fluid and one for the solid.
Yeah.
Is that right? Okay. I haven't understood very well how you can couple the two together. So how can you exchange information between the two configurations?
Okay, they communicate each other through the transfer operator, which is built from the process group that I call T. Okay, and it's based on the L2 projection and the immersed boundary. So you have fluid and the structure into the fluid. So and you have the interface boundary, and it is applied on the interface. So you consider only the values on the interface, and you apply the transfer here.
Okay, so transfer operator works only on the interface between the two configurations.
Yep.
Okay, okay, thank you. And one last question. You talk about the FSI with an active force, active stress. Okay. What does that physiologically mean? I mean, how can you translate this in your capping of the models?
Okay, so okay, you have the heart, which is covered from vessels, and you have blood inside your heart. So, and the blood represents the fluid. The heart represents the structure, and during a heartbeat, there's a contraction. For example, of the ventricle, and push the blood from the ventricle into the aorta. So you have the fluid structure interaction, which represents only the heart relaxing. But if you want to perform the contraction, you have to add an active stress,
Okay, of course.
which can be connected to the electrophysiology, because the electrophysiology is the responsible of the contraction of the muscle. So it's the first step of a fully coupled model of the heart.
Okay, so ideally it represents the stimulus given by the electrophysiology part into the FSI.
Exactly.
Thank you. Thank you, Silvia.
Thank you.
Any other questions? Okay then. Fine, Silvia. Thank you again.
Yeah.